Hello, we continue our lecture on physics-informed machine learning. In this lecture, we're going to look at a different case study, chemical reactions in this case, and we are going to look at a different machine learning technique. So if you remember the initial introduction we had, we were looking at rock candy crystallization, and I explained that it grows at a rate that is typically depends on the concentration, temperature, humidity, other factors. In fact, for any other chemical reaction, for example, if you put color droplets into water and the diffusion takes effect, and then after a while the color becomes homogeneous, it takes time for that reaction to happen. So in any chemical reaction, there is time associated with that. There is a kinetics rate associated with that. Typically, we are interested in the rate of reaction, which is basically a derivative with respect to time. So let me give you a more concrete example. If you look at the 5 minutes epoxy glue, you combine part A and part B. And then you wait, and generally after 5 minutes, it should go from a viscous glue into a solidified glue. And it takes, let's say, 5 minutes for that thing to happen. During that time, you can think about it this way, that there is a degree of reaction, let's call it x, that changes from 0 to 1, and that's this red curve here. Basically says when it's 0, we have a completely viscous liquid. And when this goes to 1, it has transformed into solid. So how long it takes to go from 0 to 1? 5 minutes. And specifically, what is the speed that these things happen? It's not a constant speed, it's a different rate. If you look at the derivative of this degree of reaction as a function of time, initially the speed is slow, and then it picks up and goes to a maximum reaction rate and then drops down. It implies a very specific reaction that is happening here. We are very interested in the shape and also the equation that describe that rate of reaction. So in this case, in this case study, you're going to learn if you have data. In this case, let's say we have this blue curve. And data is typically a function of time. So as time goes by, you're measuring something. Can you represent that using some sort of closed form equation that then gives you some higher level understanding of that physical phenomenon? So that's the main aim here. So I'll give you a bit more background in reaction rates, and then we're going to apply a different approach of physics-informed machine learning we call SINDy here. For the type of epoxy that I mentioned, it comes from our understanding that this speed of reaction is reaction rate dx over dt depends on both temperature and degree of reaction itself. We're going to put aside the dependency on temperature. What we're interested here is this. If you have some experimental data, this red curve for the speed of a chemical reaction, can you tell me its dependency to the degree of reaction itself? So in a way, if dx dt is a function of x, what is that function? So what is the closed form equation that we have here? We have some understanding of these closed form equations for chemical reactions. There are some reactions that they slow down as time goes by. It's a deceleration type reaction. You can represent those behavior of 1 minus x to power n. Let's say n is 2 or 3, for example. X increases, that value drops. And again, x is between 0 and 1. Some reactions, as the reaction goes further, it provides more site for reactions. So the speed goes up and up and up. It's like x to the power m. Some reactions, like the one that we saw for epoxy, the reaction goes up and then drops down. They can be represented with x to the power m, 1 minus x to the power n. And again, m and n could be, like, say, 1 or 2 or 3 in that range, or other types of reaction. So our aim here is to figure out if an experimental data for a reaction is given, what type of this closed form equation represent that reaction. Typically, this is what we do. We do some sort of tests. In this case, if you're familiar with this, is called DSC test. Out of these tests, you're basically measuring dx dt as a function of time. And then not only we want to figure out what type of fx governs that equation, x to the power of m1 minus x to the power of n, we're going to figure out what are those m and n as well. So that also tells you something about the underlying physics. But think about it this way again. You have some dynamic data, typically a derivative of something that changes in time, and you want to represent that with some components that you're measuring, or maybe derivative of the components that you're measuring. But the aim is to create a closed form equation at the end from data. I give you one other specific example. If you look at the Boeing 787, the epoxy that is used in Boeing 787 is a very specific epoxy. The reaction rate is quite complex. It's sort of can be in an approximate way can be represented as adding some of these base level components together. There is more information provided in the reference here. And the idea is this: if the reaction rate of such epoxy is provided, can you come up with that type of closed form solution to represent that data? And how do you find that? We're going to use a specific approach called SINDy, or Sparse Identification of Nonlinear Dynamic Systems. My good colleague Steve Brunton has quite a few videos on this, and there are references here for you to look more into that. But if you search the channel, you will find more information about SINDy approach. But the whole idea of SINDy is something like this. You have some sort of observation. Let's say u changes as a function of x, which is a spatial, and t, which is like a time or a time series. And then you want to say, for example, changes of u in time is related to some sort of combination of differential equations of u with respect to x and even time itself. So this is one example provided, that you go from this observation here, which is this 3D representation, to this closed form equation. And SINDy is basically developed to take you from observation to this type of closed form equation. So again, since my colleague has provided a lot of information on this, I'm not going to go into details of that, but I'm going to provide you base level understanding of how SINDy works, and then we're going to look at the Python code implementation of SINDy. So the whole idea is that you have, let's say you have some measurement u as a function of x, which is, let's say, location, and t, which is time. First step is that you collect data. So you have a lot of data, which is u, x, and t. Then you create a library of functions. You can see some examples, differential equation based on those numerically calculated based on those initial values. We're going to use a regression approach called lasso, and it's a sparse identification. Basically, the idea is lasso. The concept is these base level functions multiplied by some constant. If you sum them up, they closely resemble the initial observation. But which one of these base function and with what constant? And this is the job of lasso, to sparsely identify those base level functions. So lasso is really good in selecting, so putting the weights of some of these functions to 0, and then selecting some sparse version of the baseline function, and also give you coefficients of how to put these things together to become your observation. Okay, so I'm going to show you how to develop the Python code for SINDy, and then I'm going to apply it to 3 problems. But these are like 3 specific relevant problems to industry applications. So there are 3 types of polymers, and there are different versions of adhesives. One is phenolic-based, the other 2 are epoxy-based, and they have different applications. In each of these cases, the reaction rate has been measured as a function of time, and we want to create that closed form solution that represents the reaction rate. The first adhesive is quite widely used in aerospace. The second adhesive, Hexyl 8552, can be used in different applications, like making, let's say, epoxy-based tools. And the third adhesive is the one which is used in Boeing 787. It's called Torre 3900-2. So we're going to look at how SINDy can be used to extract the differential equations for each of these reactions. So first of all, 3 CSV files are provided for you. Each of them for the test data from one of these materials. If you put all of them together, you have this curve here, which is the degree of reaction changing from 0 to 1 as a function of time. And the other ones are the reaction rate, which is the derivative of the degree of reaction versus time. And again, the idea is to take this data, which is the derivative of degree of reaction, and fit a closed form equation to that. The implementation. So the Python code implementation is like this. First, you create a baseline, to create a library of functions. So here we are creating, based on our understanding from the literature, we are creating functions which are either 1 minus x to the power n, where n is the specific values, and these are coming from the literature. We do x to the power of m, again, m with the specific values, x to the power of m, 1 minus xn, and a logarithmic function which represents diffusion. So this part of the code, which is a function within the code, creates all of these functions. So it basically loops through every function, changes m, and creates this function and adds it to the library. We are using a Python library called PySINDy. So you can basically call PySINDy. And then we also bring the lasso optimizer, which I mentioned we needed in this technique. And the other ones are quite typical libraries. Some for handling the data and then plotting the data at the end. The approach is quite simple. You prepare the data, you define the lasso optimizer, and one of the key factors it affects your calculation is the value of alpha, which is the weight function which is added on lasso. So basically, lasso starts to eliminate some of these functions in the library, and this lambda affects the rate of how fast it eliminates some of those things. So it becomes quite sensitive parameters. You fit the model, and then you report the score of the fitting. So let me walk you through the 3 examples I gave. The first example, which was a phenolic-based material, the SINDy's fitted functions is given here is 1 minus x to power 1.3 or 1 minus x to power 1.5. So in order to see the 2 components, I have plotted them together. So basically, there is this original data and predicted data. They're completely superposed. You can't see the difference because we have almost 100% accuracy. And then it shows you some of the functions from the library and the coefficients that it got from those. So putting aside some of the ones that have very low coefficients, there are 2 functions that have high coefficients, and these are 1 minus x to the power 1.3 and 1 minus x to the power 1.5. The hidden solution that created this function was 1 minus x to the power 1.37. You can always go back to increase the number of base functions in SINDy to have more of these 1 minus x to the power m. But I mean, this is quite clear that it indicates that the rate of reaction is related to 1 minus x to the power of m, and m is somewhere between 1.3 and 1.5, which is very close to the final solution. In the second example, again, similar to the previous example, you can see the curve here. And then the 2 functions that the SINDy has identified, both of them are in the shape of x to the power of m and 1 minus x to the power of n, which is close again to the final solution, the hidden solution that was used to create this. And you can kind of see again that both the m and n, which is between 0.67 and 0.75 and between 2 and 3 are close to the final parameters that we have to find. So in a way, not only it finds the base functions, it also finds the power that dictates the rate of the reaction in different directions typically. So the last one, which is a bit more complex function, is following the same example. It's for the example I mentioned for Boeing 787 epoxy-based material, it finds an equation which is 1 minus x to the power plus x to m and 1 minus x to power. And you can kind of see if you put these three functions together, you more or less get this shape that we want to predict. So not only it figures out that there are two types of reaction, again, it finds the powers. And if you look at the hidden solution is also following the same logic. There's a 1 minus x component that creates this deceleration type behavior, and there is x, 1 minus x to the power that creates this acceleration, deceleration.